Okay, so in this training module, we'll be looking at module 6, which is to do with heat exchanger tube fouling. So what we're doing is we're using warm 40-degree water to condense low pressure steam through a heat exchanger. So this is a diagram of the system we're trying to build, and let's get started. So we want to create our fluid sources and our fluid sinks. Fluid source is going to be 40-degree water. Oh, that already exists, so I'm going to call this 40 water. And then we're going to create a fluid sink here, and this is going to be a 0 bar gauge sink, atmospheric. And then we want to start constructing our line. So we add a new line. We want to use a standard connection size of DN200 schedule 40 pipe. And we can leave that in the default starting position. And our source here is that, what was it, 40 water that we created. Alright, so during this we're going to need straight pipe sections. We're going to need 90-degree bends. We're going to need an orifice with 101mm internal diameter, and we're going to need a valve to control the flow. In this we'll be using a globe valve. We can leave the default curves and things, and I'm actually going to make these out of stainless. We also want a pump. This will also be made out of stainless steel, and we want to create our heat exchanger. This heat exchanger will be using DN25 schedule 40 pipe, it says in the problem description, and we're going to make it multiple tube rows with a tube sheet connection, triangular tube pitch, and a circular tube bundle with a domed end cap. The bundle diameter is going to be 1 meter, and the tube length is 10 meters. That should give us the expected 58 tubes. So now we actually want to build the system following that diagram. So from our source we can have a meter of pipe, and then our pump. Then we'll add another meter of pipe, turn north, meter of pipe, and then our valve to control the flow. Another meter of pipe, then the heat exchanger. And then this is where we turn back around, turn right, add a meter. I'll edit that to be a bit longer so that we can get away from the heat exchanger a little bit. Another pipe, and this wants to bring us back close to the source. Then we can add in the orifice and the sink. So here we have the system. Now we want to add the steam that'll be surrounding this box. So we right click and edit, and we want to add here a, oh, that's gone away. Here we go, a water steam process tube. So the pressure of this given in the problem is 1 bar gauge, and it'll be exposed to the whole heat exchanger. And there, that's lined itself there. Okay, so here we have what we have created. Under normal operating conditions, what is the maximum cooling water temperature, and by how much do the heat exchanger tubes expand when going from ambient to operating temperature? So we click on the play button to solve this one, and it gets us some results. We can see the cooling water moves at 160.8 tons per hour, but what we're interested in is this result graph. So you click on this and you can look at your fluid temperature here. We want to look at the maximum. So we can see that the maximum is 91.8 degrees. And the second part, by how much the heat exchanger tubes expand when going from ambient to operating. So right click on these heat exchanger and we click properties. I'll move that so you can see it. And we can see that the tubes are 10.009 meters. And if we unclick this, the tubes are 10 meters at ambient temperatures. So we can see they expand by 9 millimeters. Second question, if a fouling layer equivalent to 1 millimeter of cement is present on the cooling water side of the tubes, what is the expected reduction in steam condenser capacity? So if we add this fouling layer to the tubes first, right click edit, and you can click on this bit here to do the pipe lining. We want an external cladding layer with a thickness of 1 millimeter of cement. And if we zoom in, we can see that that's happened to all of them there. We want to resolve it. And we're looking at the reduction in capacity. So there's 161 tons an hour going through. And we can see that the heat gain now is just less than 4,000 kilowatts, 3,950 kilowatts. And before, we can look at what that was. If I remove the cladding and we solve it, you can see that that was up at almost 10,000 kilowatts, so it's a big difference. So now we're going to see if we can counteract this. I'll put the cladding back on. 1 millimeter of cement. And this time we're going to see if we can increase the flow rate. So I can just scroll on this or right click and edit. And we want it to be 100% open now. So if we increase the flow rate, we can have a look at the cooling capacity, which is 4,530 kilowatts, which is still less than half of what it was before. So no, we can't counteract this capacity reduction.